Hi everyone, in this video I'm gonna introduce metric space to you guys. So you might already notice that I actually have uploaded one video called like Dabble into metric space before, and the reason why I do metric space again is, well, first of all, I wanna like look deeper into the metric space thing. And also I found that, well, since I've been learning since the first video I've uploaded, and especially last semester, I also have a module uh, which is about also mathematical analysis. So I found that actually something I've introduced in my videos and which I have uploaded, there is something wrong in them in those videos, and actually actually they cannot be considered as wrong, or rather like inaccurate, because some statements I said or introduced, or some theorems only holds under certain like conditions, and back then when I upload those videos, when I shoot those videos, I actually didn't know that, and until last semester, I found that actually a lot of my a lot of things I thought would be right turned out to be inaccurate. So I decided to redo the metric space again, and hopefully I can fix some other problems in my videos, in my previous videos. Like, well, the most problematic one is the complete or compact well, yeah, compact set, I think. Yeah, compact set. So, first, first of all, we start from metric space because these are all closely correlated. So, to start with metric space, the first thing is to define a kind of like a measurement of the distance between two, say, points. But actually, the distance that we can measure are not only limited to points, but also like functions, the distance between two functions, and the distance between two like sequence. So no matter what distance we want to measure, the distance exists if it satisfies three axioms. First one, so let's say let x be a set. So we will first have set to take out elements, right? Otherwise it's gonna be nonsense. So let x be a set, and a metric we call the distance function a metric, or you can call it distance or simply a distance function. So a metric is a function d from x times x to r, because we are taking 1 point from this set and 1 point from the same set x. Such that for any x, y, z in the set x, the following holds. So since I have mentioned them before in the previous videos, I guess you already know. First one is that distance between the 2 points x and y 0 if and only if x equals to 1, and only if these 2 points coincide with each other. And M2 is that dxy is dyx. order of the points doesn't matter. And 3 is that the triangle inequality dxz is going to be smaller than dxy, smaller or equal to dxy plus dyz, right? And typically, if we are taking points from the Euclidean space, then the distance that you can use are actually, there are quite a lot of distance functions, and you can actually make up your own distance functions as long as they satisfy the 3 axioms. But typically, what I'm gonna introduce in this video is simply dp. Well, p is kind of like a variable. So p is determined by you. So if you wanna calculate the distance of the distance d1 or d2, p equals to 1 or 2, and the formula is gonna be dp equal to sorry about that. You take the sum from 1 to n, the sum of xi minus yi to the absolute value of the distance to the piece n to the piece power, and you then take the 1 over piece power. Right, so if now p equals to 1, then the distance would be simply you are taking the distance the absolute value of the difference of xi and yi. And if p equals to 2, d2 is going to be xi minus yi, the square, take the square of it, and after taking the sum, you take the square root of it, right? So so the reason I wrote it as xi yi is that, well, x and y are 2 points, but I didn't say that the points are in 1D or 2D or 3 dimension space, right? The dimension is actually n, right? Because we are taking the sum from 1 to n. So if so usually we use 2D spaces, two dimension, right? 2 dimension spaces. So usually we take suppose p equals to 2. If n equals to 2, then the distance would be, so x now is equal to x1, x2, right? And y equals to y1, y2, right? So the distance between x and y is going to be x1 minus y1 to square plus x2 minus y2. Take the square of it and add them up, and then take the square root of it. Okay. And another thing is that if p is going to the infinity is equal to the infinity of x and y is equal to the maximum of the absolute value of xi minus yi. Okay, so this is what we usually are gonna use, the dp and the infinity. And another thing that we use a lot is the distance, the discrete distance, DDIC, discrete. Discrete distance is kind of like a program, a yes or no choice. So a yes or no program, kind of like, so it says the distance is gonna be 0 if x equals y. Distance is gonna be 1 if x does not equal to 1. So it's like if you put two like equal value to the distance function, then the output is gonna be no. So if we assume that 0 means no and 1 means yes. Or actually, it's gonna be more understandable if we say that 0 means yes and 1 means no, right? So it's like you're asking a program if these two numbers are the same. If they are the same, then the output is, well, yes, they are the same. And if they are not the same, the output is going to be 1, which is no, right? So this is discrete distance. And if you're interested in the proof, you can actually check that dp, the infinity, the discrete, or satisfy these three axioms. So these are kind of like these distances are kind of like specifically for the points on the Euclidean plane, or n-dimension plane. N-dimension space. Sorry, it's not Euclidean. It's n-dimension space. So what we want to talk about further is, what if the space, what if I give you a space of sequence or a space of functions, and for space of sequences and space of functions, we also have some distance functions for them. So if we want to talk about the distance functions in the space of sequences, then the distance function is going to be dLp of the function an bn equals to, and from 0 to infinity, taking the absolute value of an minus bn and to the power of p, and then taking the power of 1 over p of the whole term. And for dl infinity, the distance is gonna be supremum of the absolute value of the difference of an minus bn, and takes from 1 to n, right? So it's actually quite similar to the distance for the points, right? And for the space of sequences, we also have some like typical spaces, or some general cases. So we have space LP, which is a space where this sequence, where sequences satisfy certain condition, are said to be in the LP space. So the condition is that the sequence an, a sequence of real numbers, such that if you are taking the absolute value of if you are taking the power of p of the absolute value of the of each term and add a map, then the sum is gonna be the sum is not gonna be infinity, so it's like it's gonna converge. But each term will be not the term itself, but by like but you first like taking the power of p of each term. So it's like where so it's like given a sequence of real numbers to justify if it's in the space LP. You first kind of like transform the sequence into like a1, the absolute value of a1 to the power of p, and a2 p, and then see if this new sequence, if this new sequence, then adding them up is actually the series, right? If this series is convergent, if it is, then the sequence is actually in the LP space. And we also have air infinity, right? For p goes to infinity. So air infinity is going to be defined as sequence such that an is bounded. So this is simply the definition of two spaces, LP and L infinity. Actually more than two, right? Because p can be 1, 2, 3, 4, or any other numbers. So okay. Well, actually there are some theorems about space of sequences, about like so these are simply spaces where a space are something that like hold kind of like a container that hold some sequences, and to be a metric space, the space have to equip with a distance, right? And well, immediately for LP, you can imagine that DLP is gonna be the metric for this space, but is it the only like distance for the space? Well, absolutely not. And actually, we have a theorem saying that for p smaller or equal than q, or p smaller or equal to q, smaller than or equal to q, LP is gonna be contained in LQ. This theorem is only about the spaces LP, LQ, and to combine with the distance, we actually have that for p smaller than or equal to q, LP DLQ is actually a metric space. And well, if you know this theorem, this is kind of like a corollary, right? Corollary. I don't know. Corollary. Well, because LP is the subset of LQ, and we know that DLQ is a metric for LQ. So naturally, it's a metric for LP, right? Because every element in LP is contained in LQ, and they satisfy the distance function for LQ. So LP must also satisfy the elements in LP also satisfy the distance function DLQ. Oh, well. So this is about space of sequences. So in the next video, I'm gonna continue to show you the space of functions and also product matrices, not matrix, matrices. So, okay, so see you in the next one.